In 4.2, we are going to review some more about writing equations for chemical reactions, and we'll get into the net ionic equation, which a lot this year, instead of writing the whole equation out, we want to just write the net ionic equation. So a chemical change involves a reorganization of the atoms in one or more of the substances. This process is represented by a chemical equation with reactants on the left and the products on the right. Right? We learned this in Chem 1. So the reactants are what you start with, the products are what you go to. So I have the formation of water as an example of that for you. Notice in chemical equations that the atoms have been reorganized, so the bonds have been broken that are holding the compounds together, and new ones are formed. It's important to remember that in a chemical reaction, atoms are not created and they're not destroyed. So all the atoms present in the reactants must be accounted for among the products. They're just rearranged. So in order to see this, chemical reactions must be balanced. The chemical equation for a reaction gives two very important types of information. It gives us the natures of the reactants and products and the relative numbers of each. So when I say nature, we're talking often about the physical states. So solid, liquid, gas, or aqueous. And then the relative numbers of each come from balancing. So we use coefficients in front of the numbers. You have to be careful with these words, okay? So the coefficients are the numbers that go in front of each of the compounds to help give it balanced. And this is the relative number of reactants and products. So then we could then move this into mass, moles, molecules, liters, pressure, all kinds of things with stoichiometry, which we'll get to a little bit later. But just all review of Chem 1, we just need to make sure we still know how to do it, okay? Don't forget about diatomic molecules. We call them Hunkel fibers, right? But call them diatomic molecule if you have to answer a question about them. It's the same atom bonded together, and they like to be like this, these 7, because they're more stable if they're bonded than if they were just by themselves. And so these 7, like when we're breathing oxygen gas, it's really O2, not just O. So just remember those 7. I have the poster in the room still. Unless they're balanced, chemical equations are of little use to us. So make sure that you always check to make sure if you're given an equation that it's balanced, or if you have to write it, that it's balanced. So the identity of the reactants and products are not changed when it's balanced. All you have to do is make sure that the number of atoms is the same. So you don't change the formulas, meaning the subscripts, the little numbers. You only can add the coefficients in front. So just some little hints about balancing equations. Remember what reaction is occurring, what are the reactants, products, what are their physical states. Usually you might need to include that this year. Write the unbalanced equation, then you balance it by inspection, starting with the most complicated molecules. And then you want to make sure that you have the most reduced you can possibly have for all the coefficients too. Because later on, that will make things easier. Okay, so we have chromium compounds exhibit a variety of bright colors. When solid ammonium dichromate, which is a vivid orange compound, is ignited, a spectacular reaction occurs. This is actually really cool, and I have some in the room, so maybe like the day before spring break or something, I'll show you guys. Although the reaction is somewhat complex, let's assume that the products are solid chromium oxide, chromium 3 oxide, nitrogen gas, and water vapor. Let's write the equation for this reaction. So we haven't talked about it yet, we're going to in just a second, but this is a decomposition reaction. So we have the solid ammonium dichromate, which is the NH4 to Cr2O7, and that is ignited, breaking into the product's solid chromium 3 oxide. So remember, the 3 tells you the Roman numeral tells you the charge, not how many, and oxygen has a -2 charge, so that compound will be Cr2 2O3. If you don't remember how to write ionic compounds, we're doing that in Chemistry 1 right now, so I have lots of stuff to help you with that. Nitrogen gas, and that is going to be N2 because nitrogen is one of the 7 diatomic molecules, and water vapor. Okay, so we just want to make sure that this equation is balanced. Well, my first check, the nitrogens are good, but the hydrogens, we have 8 on the reactant side, and we only have 2 on the product side, so we're going to put a 4 in front of the water, and that makes 4 O's plus these 3 makes a total of 7, which is good for the oxygens on the other side, and 2 chromiums. So that's all we have to do. So just remember, like, it's not always going to be super complicated to balance an equation. You just have to remember how to do it. Okay, so in Chem 1 we learned about the 5 types of reactions: combination, decomposition, single replacement, double replacement, and combustion. I think combustion is the only one that I don't have pictured there. Remember, combination, you're combining to find one product. Decomposition, you have one reactant breaking down, like a decomposing body. Single replacement, you are replacing just one of the parts of a compound. And double replacement, remember, it's the outsides together and the insides together to predict what the 2 products will be. And combustion, most of the time, the products are going to be CO2 plus H2O. Carbon dioxide and water. You could call it water liquid or water vapor. I've read different things about that. Some people say it's liquid, but then there's so much heat produced from a combustion reaction that it instantly turns to vapor. So I wouldn't take off either one that you label it for that. So in combustion reaction, it's going to have a hydrocarbon, so something with C's and H's, if it's going to produce those products. Okay. Sometimes we have cases where they are combustion reactions, but it doesn't produce that. And the other way that you can tell it's a combustion reaction is that one of the reactants might be O2. So if it combusts with oxygen from the air, that would be another example. So these are the 5 that we learned in Chem 1. Okay. If you don't remember how to identify these types, I will link some videos from the Chemistry 1 library of videos to help you with that. But in Chem AP, we are going to focus on not really so much on those 5 types, but we have some other types that those 5 fit into. And so we have to just know what those 5 background ones are. So first we're going to focus on reactions in solution. When we have reactions in solution, we also often form a solid or an insoluble substance, which is called a precipitate reaction when this happens. So remember, the precipitate is the solid that's formed from the reaction. When writing these equations, we must know the identities of the reactants and products as well as their states of matter. So the products and their states of matter can be predicted because in virtually every chemical reaction, when a solid containing ion dissolves in water, the ions will separate. So this will get us into writing net ionic equations and all that kind of stuff. To predict the products, understanding ideas and remembering key chemistry information is required. For example, some of the things that you might need to remember: how to write correct formulas. Remember, balance those charges to 0. Solubility rules, which are in the next slide. The product's form should be different from the reactants that you started with. So if you ever write the same thing twice, you did it wrong. Okay? So if you're having trouble writing in reactions, let me know. The solubility rules are listed here. They're on page 156 in your textbook if you're ever working in homework and don't have your notes. It's said that you need to have a general understanding of solubility rules, but that you don't have to have them all memorized. It's really, just note that, like, number 1, if it ever has nitrate, it's going to be aqueous, right? So soluble means aqueous. And number 2, if it has potassium or lithium, alkali metal is the group 1A metal, and ammonium, then it's going to be soluble. Okay? And then the rest of them have exceptions. which means that most of the time they're one way, except if it's in those certain cases. So if it's an exception, like on a question, it might tell you what that is. But those are here for you to remember and to use. Okay. Remember, slightly soluble means that a tiny amount of the solid can dissolve, but it's not noticeable. So we won't be able to tell that. So we would label insoluble and slightly soluble both as just solid in our labeling of the states of matter. Okay, so using solubility rules, let's predict what will happen when we mix the following two solutions. So the first one is potassium nitrate and barium chloride, and the second one is sodium sulfate and lead 2 nitrate. Okay, so I'm doing A first. Okay, potassium nitrate, potassium has a +1, nitrate has a -1, so that is KNO3. And these are all solutions for the reactants, so that means I know it's going to be aqueous for both of the reactants. Okay, and that's mixed with barium chloride. Barium has a +2 charge, and chloride has a -1, so that'll be BaCl2, and I know it's aqueous because it's the reactant. Okay, so now if you haven't figured it out yet, this is a double replacement reaction. So we have to take the outside ions together and the inside ions together. Remember that when we do that, you revert back to the originals. Okay, so the potassium and the chloride are going to go together, and that's the K+1 with the Cl -1. So even though there's a 2 by the barium chloride, that 2 doesn't carry over. So we would have KCl for that, and then the other product is going to be the barium with the nitrate. Positive ion goes first. Barium has a +2 charge, so we would put nitrate in parentheses. Okay, so now by not carrying over the subscript, now we have an unbalanced equation, so we do need to balance that, and to do that we would put a 2 there and a 2 there. Last but not least, we want to predict what happens. So basically, are we going to create a solid or not? Okay, well, looking back at the solubility rules, we know that anything with a nitrate is soluble. So that tells me that the barium nitrate is going to be aqueous. Okay, and then in number 2 of the solubility rules, it says that anything with a potassium is going to be soluble as well. So that means that the KCl is also aqueous. So in A, this reaction, there's no solid form, so this is not a precipitate reaction. Okay? Now let's do it for B. Sodium sulfate and lead 2 nitrate. So sodium has a +1, sulfate is SO4 -2, so that'll be Na2SO4. We know it's aqueous because it's the reactant and it told us they were solutions. Okay, and lead 2, remember the Roman numeral tells you the charge, so that'll be Pb with a +2 charge, and we know nitrate has a -1. So that'll be PbNO3 aqueous. Okay, so now, same thing, this is a double replacement, outsides and insides together. Remember, we don't carry over subscripts, so we would revert back to the original ions. So we would have Na go with NO3. And then the Pb with the SO4, Pb goes first. That's a +2 -2, so they just cancel. So there we go. Now, it is not balanced. To balance, all you do is put the 2 in front of the sodium nitrate. And then now, based on solubility rules, I know that sodium nitrate is going to be aqueous because that's a double whammy right there, rules 1 and 2. Now let's look back at the sulfate rule. So sulfate rule is number 4. Most sulfates are soluble except if it contains lead sulfate. Then if it's an exception to the soluble rule, that means that that would be insoluble. So then we would label the PbSO4 as a solid. Okay, so hopefully this is just review and it's coming back to you not too bad. Okay, the 3 types of reactions that, or 3 types of equations that we can use, especially for precipitation reactions, are the formula equation, which is sometimes called a molecular equation. We called it that in Chem 1. This is the regular chemical equation. So if you need to make a little note to yourself, this is just the regular equation. that we will have. It not necessarily the actual forms of the reactants and products, but it's the basis for everything else. Now, the complete net ionic, or the complete ionic equation represents as ions all the reactants and products that are strong electrolytes. AKA, as ions, means that anything that is aqueous gets broken up. And since it is an ion, it needs a charge. Okay? This is something that I was very stickler about in Chem 1, that if it's an ion, you have to have a charge on it. We were doing a pretty good job this year so far, so let's keep that up. And then the net ionic equation includes only those solution components that are undergoing a change. So basically, it's going to be the ions that make up the solid product. Okay? Spectator ions are not included. So in Chem 1, we wrote out the complete ionic, and then we crossed out the spectators. It's the stuff that's the same on both sides, both in ion form on either side of the equation. Eventually, you would like to be able to just write the net ionic without doing the rest of the work, but until we see that, we will practice all the way through. Okay, so we want to write the formula equation, the complete ionic equation, and the net ionic equation for the reaction between aqueous potassium chloride and aqueous silver nitrate. I'm going to flip to the next page. Okay, so just to label them, I'm going to put M for molecular, and then C for complete, and N for net ionic. Okay, just to help us out. So the M is just writing it normal, right? So we have potassium chloride, which will be KCl, aqueous, plus silver nitrate. If you forget, silver has +1 charge, so that'll be AgNO3. Okay, and this is double replacement, so outsides and insides. The outsides will be KNO3, and the insides AgCl, because silver will go first. Isn't it nice how everything's just a +1 -1, so it's already balanced? That's wonderful. Okay, based on solubility rules, this potassium nitrate will be aqueous and the silver chloride will be solid. You cannot do the complete ionic and the net ionic unless you have a solid, or unless you have something that's not aqueous. Okay, so that's your hint that you are doing it correctly. And remember, soluble means aqueous. Okay, so now for the complete ionic, everything that has a Q will be broken apart into its ions, and every ion needs its charge. So we have K +1 aqueous plus Cl -1 aqueous. So that was the potassium nitrate broken up. Plus, now we break up the silver nitrate, or sorry, the potassium chloride. Alright, so there's the silver nitrate. Okay, and we're still keeping things on the correct sides of the equation, so now we break up the potassium nitrate, because that's labeled as aqueous. And then now, this solid stays together. So that's the whole point of it being a solid. It doesn't dissolve. So it needs to stay written together as well. So the AgCl solid keeps the exact same as the one before it. Okay, so then now, in net ionic, what we did in Chem 1 is after looking at the complete ionic, we said, oh, look, the sodium or potassium's on both sides, so we can cross that out. And the nitrate's on both sides, so we can cross that out. Those that we cross out are the spectator ions. And then the net ionic is what we write everything that's left. And so the way that you'll be able to start predicting the net ionic without doing all this extra work is the net ionic are the two ions that form the solid. Okay, so if you are done and it's not in the correct ratio to form the solid product, or you don't have the correct solid left or something like that, then you did something else wrong. But eventually we should be able to just do that net ionic only.